In this video, I'll give an introduction to derivatives. And specifically, I want to focus on two aspects of the derivative. First, derivative as an instantaneous rate of change. And second, derivative as a slope of a line tangent to a curve at a particular point. And these are really two aspects of the same thing, but approached from different perspectives. To understand derivative as a rate of change, as an instantaneous rate of change, we need to know what an average rate of change is. An average rate of change measures, on average, how fast a quantity changes or was changing over a period of time. For example, if I start with no money in the bank and 10 days later I have $100, then the balance in my account has increased by an average of $10 a day. Did I actually put in $10 each day, or did I put in all the money at one time on a particular day? The average doesn't tell us that. It simply says that on average, the balance in my account increased by $10 a day. Now, an instantaneous rate of change, however, measures how fast a quantity is changing at an instant in time. And we're going to see that an instantaneous rate of change is really nothing more than an average rate of change where the elapsed time is minimized until it is essentially zero but not zero. Second, to understand derivative as a slope of a tangent line, we first have to know what a secant line is and how to calculate the slope of a secant line. Now, you may recall from geometry that a secant line is a line that intersects a circle at 2 points on its circumference. A tangent line is a line that intersects a circle at exactly 1 point on its circumference. Now, we aren't going to be concerned with circles here, but we'll apply the idea of a line passing through 2 points on the graph of a function and a line intersecting with exactly 1 point on the graph of a function. More importantly, we want to consider the slopes of these lines. Now, you may recall from algebra that the slope of a line is a rise over run, or the change in y over the change in x. With secant lines, this is easy to calculate because we have 2 points. But we run into a problem with tangent lines because we're dealing with only 1 point. Now, to address this, we're going to see that a tangent line can be viewed as a secant line where the 2 points are moving closer and closer together until they are essentially 1 point, but not 1 point. Now, let's begin with a few questions. How do we know how fast Tin Lincecum's pitch was traveling at the instant this picture was taken? Or how do we know how fast Usain Bolt was running, the moment pictured in the photograph here? How do we know how fast General Lee, the Dukes of Hazzard's car, was flying through the air as it approached the building in this picture? How do we actually know that any of these objects were moving at all when the pictures were taken? Well, in order to answer these questions, we need to establish some principles from physics. How do we know something is moving? Quite simply, if an object changes position, then it has moved. And how do we know how fast it was traveling? Well, if the car traveled 100 feet in 5 seconds, we take the ratio of distance traveled to elapsed time, and that gives us an average velocity. In this case, 100 feet divided by 5 seconds, or an average velocity of 20 feet per second. What we need now, though, is a scenario that's going to allow us to move from average rates of change to instantaneous rates of change. And fortunately, due to gravity, we have a phenomenon known as free fall. We're going to simulate dropping a coin from the top of the Empire State Building, 1,250 feet above the ground. And physicists tell us that if we assume certain environmental factors, the height of the coin can be found using the formula h of t is equal to negative 16t squared plus 1250, where h is the coin's height above the ground in feet, and t is the time in seconds after it is released. Now, what you see on the screen is a graph that will be used to simulate the fall of the coin, another graph of the height of the coin over time, which will form a parabola, and a table of values. And these will give us 3 different perspectives on the fall of the coin as it moves through the air second by second. At time t equals 0, the coin has just been released, and so it is exactly 1,250 feet above the ground. At t equals 1, the function tells us that the coin will be at 1,234 feet above ground. Since we now have two data points, we can calculate the average velocity from 0 seconds to 1 second. And we do this by dividing the change in position, 1250 minus 1234, or 16 feet, by the change in time, 0 minus 1, or negative 1 seconds, for a ratio of negative 16 feet per second. Now, since velocity has direction as well as magnitude, the negative value simply tells us that the coin is moving downward. Don't let this confuse you. Also, we're subtracting down from t equals 0 to t equals 1 instead of vice versa, because this will make our explanation a little easier later on. I realize that as we go from t equals 0 to t equals 1, we're actually going up by 1. And as a coin moves from a height of 1250 to 1234, it's actually going down by 16 instead of vice versa. But either way, the average velocity will come out the same, so don't be worried about that either. Now, this is a lot of information to grasp in a short time, but remember that you can pause at any time and replay sections that you need to see again. What is significant here is that when we draw a line through the points 0, 1250 and 1, 1234, or what we called a secant line earlier, the calculation for the slope of that line would be exactly the same calculation for the average velocity between t equals 0 and t equals 1. So this brings us to the very important idea that average rate of change of a quantity between 2 points in time is equivalent to the slope of the secant line connecting those points on a graph. This is very important. So let's go on then. At t equals 2, the object is now at 1,186 feet, and the average velocity between t equals 1 and t equals 2, calculated the same way we did previously, would be negative 48 feet per second, and this is equal to the slope of the secant line passing through 1, 1234 and 2, 1186. What is vital to see here is that the coin is moving faster as time goes on. Since the motion of the coin would be smooth, not jerky as it falls, this means that its velocity is constantly changing, and it raises the question, how fast is the coin actually moving at a particular point in time, let's say at t equals 3 seconds. But more on that later. Let's move quickly through the rest of the data and come back to that question when the coin hits the ground. Remember that you can pause at any point and verify my calculations. So you'll see that at time t equals 3, the height is 1,106 feet. The average velocity from t equals 2 to t equals 3 is negative 80 feet per second. From t equals 3 to t equals 4, it would be negative 112 feet per second, and again this is the same as the slope of the secant line connecting those points. Between t equals 4 and 5, the average velocity is negative 144 feet per second. Between t equals 5 and 6, the average velocity is negative 176 feet per second. Then between t equals 6 and t equals 7, the average velocity would be 208 feet per second, always changing, always speeding up as it continues to fall. Now, you can see this in the simulation graph because the coin is falling a greater distance for each constant 1 second change in time. Now, between t equals 7 and 8 seconds, the average velocity is negative 240 feet per second, and at around 8.84 seconds, the coin will finally hit the ground. There's a lot of information. Take your time, pause, and review as needed. Now, back to our burning question here. How fast was the coin moving at exactly 3 seconds? How about we look at it this way? If the slope of the secant line gave us the average rate of change, then the equivalent to the instantaneous rate of change would be the slope of the tangent line, as pictured here. The problem, as I mentioned earlier, is that a slope requires 2 points, and here we only have 1. And that would give us something that looks like 0 over 0, which at best is undefined and gives us no meaningful information to answer our ultimate question. So now I want to return to something I said near the beginning. We can view instantaneous rate of change as an average rate of change over a smaller and smaller period of time. We can also view the slope of a tangent line as the slope of a secant line where the points are moving closer and closer together, so that there's only an infinitesimal difference in the values of their independent variable, in this case t. So let's see how it works. We're going to use the same calculation, keeping the value t equals 3 and h of 3 constant, and moving the second data point, starting from t equals 2, h equals 1186, closer and closer to 3, and whatever the height calculates to be. So we're going to jump quickly to t equals 2.9. Here we have only 1/10 of a second difference between the two data points, and we can see that our average rate of change is negative 94.4 feet per second. When we go to 2.99, which is a difference of 1/100th of a second between our data points, we get negative 95.84. We're going to continue to move on until eventually our difference in times is at 1/100,000th of a second, and you can see that our average rate of change, or the average velocity, is moving closer and closer towards negative 96. When we get to just 1/1,000,000th of a second difference between our data points, the calculator can no longer distinguish between the actual value and negative 96. So from this point, no matter how many 9s we add on to the end of that, the calculator will say the average velocity is negative 96 feet per second, and this is what we'll call the instantaneous velocity, or the instantaneous rate of change of this function at t equals 3 seconds. Now, amazingly, this whole process of taking the ratio of change in distance over change in time with smaller and smaller time changes works out perfectly mathematically as well, but it involves a construct known as a limit, and this is something that is usually taught at the beginning of a calculus course, so we'll only briefly discuss it here in an introductory way. So how does the math work? Well, what we want to do is work through the process that we just did, but not have all those to make all those intermediate calculations. Essentially, what we want to do is to find the average velocity as the time between two data points becomes infinitesimally small, basically 0, but not 0. Get it? Here's what it looks like. We have our formula, which is essentially the slope of a line between a fixed point and a variable point. Then we want to evaluate this ratio as the value of the independent variable approaches but doesn't become 3. So watch what happens as we substitute the formula and the value of h of 3 and begin to simplify. When we factor the numerator and then we cancel factors with the denominator, we end up with negative 16 times the quantity t plus 3. Since we want to get t closer and closer to 3 until it's essentially 3, we can just set t equal to 3 at this point. There's no more denominator, and so we don't have to worry about the denominator becoming 0. When we simplify, we get exactly negative 96 feet per second. So what we end up with is a derivative, an instantaneous rate of change, a slope of a tangent line. So I hope you've found this video helpful. If you have any questions or suggestions, or if I made any mistakes, please let me know and I'll address them in future versions of this video. Thank you.